Welcome to Math GPT. Today, we're going to explore Green's theorem, a fundamental result in vector calculus that connects line integrals and double integrals. Green's theorem is a powerful mathematical tool that relates a line integral around a simple closed curve to a double integral over the plane region bounded by that curve. This theorem provides a way to convert between these two types of integrals, which can significantly simplify our calculations in various applications. Let's formulate Green's theorem mathematically. Let C be a positively oriented, piecewise smooth, simple closed curve in the plane, and let D be the region bounded by C. If P of x, y, and Q of x, y have continuous partial derivatives on an open region containing D, then the line integral around C of P dx plus Q dy equals the double integral over D of the partial derivative of Q with respect to x minus the partial derivative of P with respect to y, dA. Let's break down what this means. C is traversed counterclockwise, positively oriented. The line integral computes a quantity along the curve C. The double integral computes a quantity over the region D. Green's theorem gives us a way to convert between these two integrals. Green's theorem can also be expressed in vector notation, which helps us understand it in terms of physical concepts. Let f of x, y be a vector field with components p and q. Then Green's theorem can be written in terms of the curl of f. The curl form states that the line integral of f dot d are around the curve C equals the double integral of the curl of f dot k over the region D, where k is the unit vector perpendicular to the xy plane. The curl of f dot k is precisely the partial derivative of q with respect to x minus the partial derivative of p with respect to y. Physically, this form relates the circulation of the vector field f around the curve C to the total curl of f over the region D. You can think of the curl as a measure of the vector field's rotational behavior. One practical application of Green's theorem is finding the area of a region. By choosing P of x, y equals negative y over 2, and Q of x, y equals x over 2, we get that the partial derivative of Q with respect to x minus the partial derivative of P with respect to y equals 1. Substituting these values into Green's theorem, we find that the area of region D equals 1/2 times the line integral around C of x dy minus y dx. This is a powerful formula for finding the area of a region bounded by a parametrically defined curve. Let's work through an example to see Green's theorem in action. We want to evaluate the line integral around C of x squared y dx plus x dy, where C is the unit circle x squared plus y squared equals 1, oriented counterclockwise. Using Green's theorem, we can convert this line integral to a double integral. We identify P of x, y as x squared y, and Q of x, y as x. Now we compute the partial derivatives. The partial derivative of P with respect to y is x squared. The partial derivative of Q with respect to x is 1. Substituting into Green's theorem, our line integral equals the double integral over D of 1 minus x squared, dA. To evaluate this double integral, we'll switch to polar coordinates. With x equals our cosine theta, and y equals our sine theta, and dA equals our drd theta, our integral becomes the double integral from theta equals 0 to 2 pi, and our equals 0 to 1 of 1 minus our squared cosine squared theta times our drd theta. After evaluating this integral through several steps, we get the final answer, 3 pi over 4. So the value of our original line integral is 3 pi over 4. In conclusion, Green's theorem provides a powerful connection between line integrals and double integrals. By converting between these two types of integrals, we can often simplify complex calculations and gain deeper insights into the properties of vector fields and planar regions. Green's theorem has numerous applications in physics, engineering, and mathematics, including calculating areas, work done by force fields, fluid flow, and electrical potential. Thank you for watching this explanation of Green's theorem. Remember that this theorem is a special case of the more general Stokes theorem, which extends these ideas to higher dimensions.